Hey everyone, I'm going to walk you through two different ways of making a single buffer. So let's say we want 1 liter of 200 millimolar citrate buffer with pH of 4.0. Now, one thing to note about citrate is that citrate is a triprotic buffer and has 3 different pKa's. So if we want a pKa of 3.1, that's the lowest pKa. So citrate, that's where it's going to be in equilibrium between its fully protonated or its citric acid form and the citrate with a single minus or with 2 protons attached. And so that will be monosodium citrate, and that's because one sodium is going to ionically bond with that negative charge. All right, so we've established that we're going to be hanging out at this first pKa, and I've kind of given it away there, but there may be times on an exam where you're given a diprotic or a triprotic buffer, and based on the pKa's and the buffers available, you're going to have to figure out which ones you need to use and use common sense there. Okay, so if we are going to make a buffer from 2 different solutions of the acid and the conjugate base, this is how that process is going to work. All right, so the first things first. We're going to have citrate and its citric acid or its acid form and in its sodium citrate or conjugate base form. But before we can figure out how much we need of each, we need to figure out how much total citrate we need. And so the way we figure that out is if we need 1 liter times 200 millimoles per liter of total citric acid, and I'm going to do citrate with a minus there to abbreviate that it's any kind of citrate or citric acid. We get that we need 200 millimoles of total citrate or citric acid in the buffer. So that's our total need. Now, to get there, we're going to have to figure out how many millimoles of monosodium citrate and how many millimoles of citric acid we need to add together to achieve the total ratio. So if we need 200 millimoles of citrate, we need X millimoles of monosodium citrate and Y millimoles of citric acid. And we can figure out what those relative amounts of millimoles are by plugging it into the Henderson-Hasselbalch equation. So we know we have so the Henderson-Hasselbalch equation, recall, is pH equals pKa plus the log of the A minus over the HA. In this particular situation, it's going to be a pH of 4.0 equals a pKa of 3.1 plus the log of the concentration of the A minus or the citrate over the HA or the citric acid. So we can solve for the ratio between the two by subtracting 3.1 from both sides. We get 0.9 equals the log of A minus over HA. And then to isolate for the ratio of A minus to HA, we can raise 10 to the both sides because that will cancel out the log. And then we get a value of 7.9 is equal to A minus over HA. Now, that alone doesn't tell us anything. We want to solve for for either the A minus or the HA first. So we can write A minus in terms of HA. So 7.9 HA is equal to A minus. Now, why does that matter? Why do we want to do that? So if we need 200 millimoles of citrate total, that's equal to the millimoles of A minus plus the millimoles of HA. And so we can sub 7.9 HA into millimoles of A minus, and I'm actually going to delete that arrow because we need that space. So 200 millimoles total is going to be equal to 7.9 HA plus HA. So 200 millimoles is equal to 8.9 HA. We divide both sides by 8.9. That means we have 22.5 millimoles of HA. So we went through all that rigmarole and rearranged one of the components in terms of the other so we could plug it in to the systems of equations there. Now that we know the millimoles of HA, we can also solve for the millimoles of A minus. So we know we have 200 millimoles total minus 22.5 millimoles of HA. That's going to give us 177.5 millimoles of A minus. Now, before you move on, you want to do what my father, the engineer, would call a Snicker test. Do these relative ratios of A minus and HA make sense? If we look at our pH, we want a pH of 4. A pH of 4 is higher than a pH of 3.1. So that makes sense because if pH is greater than pKa, the A minus or the conjugate base form is going to dominate. And in this case, we have much more A minus than we do HA. And in fact, our pH is almost at the edge of our buffering range. So it would make sense that our HA concentration, that our A minus concentration was almost 10 times that of the HA. All right, so we cancel out of the Snicker test. So let's go on and let's do our math. So we know that we need 22.5 millimoles of HA, 177.5 millimoles of A minus. How do we figure out how much we need? Well, we know that we have solutions. And if we have these solutions, to figure out how many moles we need to figure out how many mils of each of those we need to help us arrive there. So if I have 1 molar, which is equal to 1 sorry guys, which is equal to 1 mole per liter, or multiply by 1,000 to give us 1,000 millimoles of HA per liter. How many liters will it take to give us 22.5 millimole? And so if we do the math, 22.5 divided by 1,000, that gives us 0.0225 liters, or if you multiply that by 1,000 to convert to milliliters, 22.5 mils of citric acid. Now, if we're thinking about the A minus, we have 500 millimolar of monosodium citrate. So if we have 500 millimoles per liter, because millimolar is millimoles per liter, times how many liters is going to give us 177.5 millimoles. We can divide that by 500 millimoles. 500 millimoles times liter. Millimoles cancel out, and we get 0.355 liters. Or if we convert liters to milliliters, that gives us 355 milliliters. So we have a liter total, but we clearly have less than a liter of solution. So we're going to have to make up the difference with water. So to figure that out, we have 1,000 liters total, or 1,000 milliliters total, minus 355 mils of A minus plus 22.5 mils HA equals 1,000 minus 377.5 mils. And that's going to give us 622.5 mils of water. But in reality, what you would probably do is you would QS, you'd add water until you reached about 900 mils. You'd check the pH you'd check the pH, and then add enough water until you got 1,000 mils in the beaker that you were measuring with. Now, this is the approach that you would take to answering the problem if you had two solutions or like two containers of powdered acid and conjugate base, or if you had a solution of acid and like a powder of the conjugate base. And you could also, in theory, figure out how you could get the moles going from grams of the powder if you had the molecular weight readily available. But sometimes if you're making a buffer, and this is the way sometimes lazy people will do it in lab, is they'll just resuspend one form in solution and then add acid or base to get it to the right form. Or if you were in the situation where you added the acid and the base together and you didn't quite make it, you would want to calculate how much acid or base you needed to add it to get it to the right pH so you didn't overshoot. So we're going to do a situation now where let's say we start with all one form. So it's the same thing where we have 1 liter of 200 millimolar citrate buffer. But in this case, we're going to have 1 molar of citric acid and then 6 molar of NaOH. And so the first thing that we have to do is we have to figure out how much citric acid we would have to add to get 200 millimolars of citric acid in the 1 milliliter solution, but coming only from the citric acid. So we can figure that out by the M1V1 equation. So if we have 200 millimolar of 1 liter, and we are adding 1 molar, how many liters would that take? So we would need to add 200 mils of citric acid. But here's the key. If we have 1 molar of citric acid only, we can make the assumption that it's all HA. So we have 200 millimolar, but it's all HA. So the question is, how do we increase the ratio? How do we increase the concentration of A minus, but without changing the total concentration of citrate or citric acid? So how do we keep the concentration of the buffer at 200 millimolar? And the answer is by adding sodium hydroxide. And then so if we have that way, if we have sodium hydroxide, lone pair electrons on the oxygen, we'll take off that hydrogen, and then we'll have more in the A minus form, but we won't change the total amount of citrate. So how would we go about figuring out how much A minus to add? So it turns out we've already done the math, except instead of adding sodium citrate, we're going to start off with more citric acid and then convert the citric acid into citrate using sodium hydroxide. So again, we assume that we're starting off with 200 millimolar of HA. So if we have our citric acid in equilibrium with its conjugate base form and proton, if we're starting out with 200 millimoles of HA, 0 of proton and conjugate base. What we want to end with is if we go back to our ratios here, remember to get a pH of 4, we wanted 22.5 millimolar of HA and 177.5 millimolar of A minus. So we want to go for 200 millimolar of HA, 22.5 millimolar of HA, of HA into 177.5 millimolar of H plus and A minus. And so what we have to do is we figure out is the amount that the amount of millimoles that are going to change over from HA to A minus are the millimoles of NaOH we want to add to convert that amount of HA to A minus. Okay, we can figure that out by subtracting 22.5 from 200. We get a change of minus 177.5 for HA, and then plus 177.5 for A minus. And so what we then would do is that, okay, we need 177.5 millimoles of NaOH. So the question becomes, okay, we need 177.5 millimolar of NaOH, but we have a 6 molar NaOH solution. So how many mils of NaOH do we need to add to get that many millimolar? So what we can say is if we have 6,000 millimoles of NaOH per liter times how many liters will it take us to get 177.5 millimole? So we divide both sides by 6,000. And we get 0.03 liters, or if we convert that to mils, we get 30 mils of 6 molar sodium hydroxide. So again, we got 1,000 mils total minus 200 mils of a citric acid plus 30 mils of NaOH. So 1,000 minus 230 mils is we need to add 770 mils of water. But again, what we'll probably do is we'll add those two together, and you'll add water until you hit like 9/10 the volume, which is about 900 mils. You'll check the pH, adjust it as necessary, and then QS or add water to 1,000 mils. All right, so those are the two ways that you could adjust. Those are the two ways that you could calculate the pH or calculate how to make a buffer from two different ways. You could also see how you could apply the second method if you started at one pH and then had to adjust it to the other. If you have any questions, please feel free to ask.